Okay, so yeah, very pleased to have Masazumi Honda visiting us from Yukawa Institute of Theoretical Physics in Kyoto. He works on all kinds of things from supersymmetry, supersymmetric dualities and holography, localization in gauge theory, resurgence and Bravais summation, and then more recently, Monte Carlo things and lattice simulation of gauge theory. I think today he's going to talk to us about digital quantum simulation of Schwinger model. So take it away.
Okay, thank you for introduction. I'm Masazumi Honda. Although there are many logos, but I'm basically from Yukawa Institute in Kyoto University. So today I'm going to talk about digital quantum simulation of a higher charge Schwinger model with topological term. This talk is based on 3 collaborations with Vipasha Chakraborty, Yuta Kikuchi, Taku Izubuchi, Aki Otomiya, Etsuko Ito, Rento Nagano, Takaya Okuda, and Yuya Tanizaki. Okay, so let me start with the introduction. Okay, so this news was already 4 years ago, and from this, this is a bit controversial if this is really a quantum supremacy. But I got the impression from the news that resource of a quantum computer is growing well, and I'd like to consider how can we use this kind of progress for high energy physics in the future. And usually, so in media, so typical application of a quantum computer is like for security, new medicine, could be finance and so on. But in this talk, I'd like to consider different things. So I'd like to apply in future quantum computer to what actually happens in accelerator, early universe, black hole, and so for fundamental physics. And in particular, here, today, I'd like to consider application of quantum computation to numerical simulation of quantum field theory. And the generic motivation would be very, very simple. So, we usually hear that the quantum computer is a powerful computer, so we simply would like to use powerful computer. There is a specific motivation for this purpose. Although I will explain detail later, one phrase, this is a relation from infamous problem in conventional approach to numerical simulation KFT. And this problem is called side problem. I will explain this point later. But before going to details, so let me summarize our recent work. So today I'll consider a model of a quantum field theory called charge Q Schwinger model. And Schwinger model is the 1+1 dimensional version of quantum electrodynamics. And so this is a Lagrangian of this model. And so the first term is a kinetic term of gauge field or photon. And this is an electron with a charge Q. And there is also mass term of electron. And the second term is a topological term called theta term. And with theta term, it is known that it's difficult to apply a conventional approach by Monte Carlo simulation for this model. I will explain detail later, but yeah, it is known that when we consider Euclidean case, this term gives a complex action, and this gives the problem in Monte Carlo simulation. And here is a list of main results, which I will explain in detail later. And so we constructed a ground state of this model by applying some quantum algorithm, and also we computed some expectation value of operator and did consistency check and made prediction. And physically, I will also explore a problem called screening versus confinement problem and the negative Stirring tension behavior. I will also explain this later. But before going into details, so let me review some basic things. So first, I want to review. So what would be what is the conventional numerical approach to a quantum field theory? And the next, I was going to give a lightning review of quantum computation, but I think I will almost skip this point since the audience seems very familiar with the quantum computation thing. And next, I will discuss how to put a Schwinger model on quantum computer. Then I will explain what algorithm I will use. And by the way, vacuum means ground state. Yeah, this is a kind of jargon in high energy physics. And then I will explain a numerical. I will show some numerical results. Okay, so let me start with conventional numerical approach to quantum field theory. But before that, let me start with explaining what quantum field theory is. So I'd like to start with one particle quantum mechanics. And this is an operator formalism. And for this case, Hamiltonian is very, very simple. So we have a momentum and potential. And so Schrödinger equation is nothing but eigenvalue equation for the Hamiltonian, and position and momentum satisfy the canonical commutation relation. By the way, I'm taking h by equal 1. And then in the basis of position, momentum can be regarded as a differential operator. And the basic observables in quantum mechanics is some expectation energy spectrum or expectation value under some state. So this is like an undergraduate course in physics. And there is another formalism of quantum mechanics. This is called path integral formalism. So for this case, we usually work on Lagrangian formalism rather than Hamiltonian formalism. And Lagrangian is given by this. So this is a kinetic energy minus potential. Then path integral formulation is like this. So this is a formula for transition amplitude, and S is action, and then path integral is given by integral of all possible position for any t. So this is the infinite, technical infinite dimensional integral, and so mathematically this is not well defined, but physicists often use this formalism. So this is quantum mechanics thing, and so next, okay. So this is operator plus path integral formalism in quantum mechanics. So this is a summaries. And so we basically consider fixation value. And also typical observables in path integral formalism is like this. So this is a ratio of two infinite dimensional integral. Okay, so this is for quantum summary for quantum mechanics. So next, let's go to quantum field theory. So this is for quantum field theory, and for quantum field theory, Hamiltonian is functional depending on some fields defined on d-dimensional space and its conjugate momentum. So for that case, canonical computation relation is like this. So for one particle quantum mechanics, it was simply I. But for field theory case, so this is 0 if x and y is distant, and if x equals y, this is non-zero. And again, typical observable is expectation value of operator and some step. And technically, this is a kind of infinite dimensional linear algebra. And there is also a path integral formalism for quantum field theory. And typical observable is like this. So here, this is again infinite dimensional integral. And but for this time, this is an integral of all possible fields, all possible configuration of fields for all the points of space-time. And the conventional numerical approach adopts the Lagrangian for path integral formalism. So let me explain this point in detail. So people usually first consider Euclidean spacetime, meaning that we take time to be purely imaginary. Then usually we cut the Euclidean spacetime by lattice. Yeah. Okay, this is a Chinese dish made of tofu, and then since the number of points of spacetime becomes finite on lattice, then the path integral becomes finite dimensional integral. And then, so numerical task is reduced to evaluate this finite dimensional integral. And the people usually use an algorithm called Markov chain Monte Carlo method to evaluate this integral. And in Markov chain Monte Carlo, so we regard this exponential minus s as a probability, and then generate a sample based on proportional to this exponential minus s, and then we approximate expectation value as the average of samples. So this is the Markov chain Monte Carlo method. But in this method, so we assume this to be a real and positive, and this is not always true. Sometimes this can be a complex and negative number. So for this case, when this is not real and positive, at least naively we cannot directly apply this method. And the naive way to avoid this problem is called reweighting. So first we rewrite this observable in like this. So we insert one equal integral with absolute value of expression minus s. Then so we can regard rewrite the original expectation value as a ratio of some expectation value under the ensemble generated by absolute value of exponential minus s. So this is equality and completely mathematically correct. But typically this way is not useful. So especially when exponential minus s is a highly oscillating integral. So
zoom in the first equation, like on the top right, I guess you didn't want to add more integrals, right? It's more like you write e to the minus s as e to the minus s divided by its absolute value times the absolute value, right? When you multiply by one,
yeah,
I mean, the average is in the end their ratio of a single integral, right? Like it's adding one divided by one trick. I guess it's slightly differently, you know. Like, am I confused?
Really?
So I mean,
this one is one, right?
yeah, but this one is not the one below, no? Am I?
The one below on the left.
Yeah, yes. But the numerator corresponds to here.
Kind of, no?
Yeah, numerator. Yeah, so now we write But I'm rewriting like
Yes, yes, and now averaging is it's just one integral, no, if you average.
yeah. And then we regard this as an operator.
Yes.
Yes. And so this is a
That's the measure then, right?
yeah. I don't yeah. Yes. And this part can be written like this. Yes. And this part can be written like this.
Oh, I see how you think about it. Okay, now
Yeah, it's 1 over.
I understand. Okay.
Expectation items. Yeah. And so this is a completely correct mathematical equality. But if this is highly oscillating, so this is a kind of this is kind of 0 over 0. It is known that when this is highly oscillating, each factor is like exponential minus volume. So it's a kind of 0 over 0. Then we need huge statistics. So if we have a ability to accumulate infinite statistics, so this is not a problem. But practically, this is computationally heavy. So this is called the sign problem. And this is the technical point. And so let me also mention physical situation typically having a same problem. So first, if we have a topological term, the action becomes complex. And if the coefficient of topological term is not small, this gives typically a highly oscillating integral. Also, when we have a chemical potential, it is also known that the fermion typically gives a indefinite sign, and this also gives decision also gives a problem typically, and this is related to the fact that so we don't know phase diagram of early universe yet, because it's hard to term chemical potential. Also, if we take real time, the exponential minus s becomes exponential is, and basically for real time case, any system has a sign problem. But we also have another formalism of quantum field theory. If we consider operator formalism, technically the problem is not integral. So we don't have this kind of problem in operator formalism at all. And there are also various approaches within to the sign problem within framework of partial integral, but I will skip it. Okay, so let us focus on operator formalism. But life is not so simple. So there is, of course, cost of operator formalism. So first problem is that quantum field theory typically has an infinite dimensional Hilbert space. So we need to regularize it for numerical simulation. But even after regularization, dimension of Hilbert space is typically very, very large. So technically, computers have to memorize huge vector and multiply huge matrices. So it seems the computation is very, very heavy. So we may expect that the quantum computers in future may do this job. So let me consider this possibility. Yeah, and also think of what we can do. Okay. So this is I finished the explanation of conventional numerical approach to quantum field theory. Do you have a question? Okay, so next I will review quantum computation very quickly. So I think you are familiar with qubit things, so let me skip it. And there are single qubit operation, action unit operator measurement, and so on. And there are X, Y, Z gate, RX, and so on. We can consider multiple qubits. There are also controlled X and so on. And also, this is the rule of the game of quantum computation for me. There's something interesting about a combination of action of unit operator, measurement, and so on. And there are errors in quantum computers, and so I think you are familiar. And also here, I will use a simulator, practically, and simulator as a tool to simulate quantum computer by classical computer. And so this does not have a speed up of quantum algorithm, but it's useful to test the algorithm and estimate the computational resource. Okay. Okay, so I finished the quantum computation. Was it okay? I think, yeah, I think I have to spend that time for quantum field theory. Okay, okay, okay. So let me explain how to put a Schwinger model on quantum computer. Okay, and first, since the quantum field theory has an infinite dimensional Hilbert space, so we have to regularize it, meaning that we'd like to make it finite dimensional. And this is a general strategy depending on type of field theory. And somehow field theory, fermion case is the easiest for this purpose, because for fermion case, just by putting the theory on lattice, maybe space becomes finite dimension. But physically, this is essential because of Pauli's exclusion principle. But for boson case, it's not true. So if we consider scalar field, then it will put space at each. So scalar field theory on lattice is technically the same as many particle quantum mechanics, and you know that even one particle quantum mechanics has an infinite dimensional Hilbert space. So for that case, even after putting the theory on lattice, so we need an additional truncation. And also there is a degree of freedom of gauge field, like a photon. And for gauge field case, there is a difference between lower dimension and higher dimensional case. This is because of gauge symmetry. And it is known that if we consider 0 + 1 dimension or 1 + 1 dimension, we can eliminate the physical degrees of freedom completely if we consider space with boundary. But in higher dimension, we still have an infinite dimensional Hilbert space, and as in scalar field, we need additional truncation. And today, I will consider Schwinger models, and the Schwinger model does not have a scalar and has only fermion and gauge field. Okay. So let us consider Schwinger model, and this is a continuum description of Schwinger model, and Hamiltonian is given like this, and the physical so one important point is that there is a constraint on physical states. So for gauge theory, so there is a physical state, both physical states and unphysical states, and there is a condition for physical states. And physically, this is the same as Gauss law. This is the operator version of Gauss law equation. And there are symmetries in this model, and first we have a symmetry called chiral symmetry. Chiral symmetry is like phase rotation of fermion. So this is something like this. Here, gamma 5 is some matrix, and makes sense. And this symmetry appears only when mass is 0, and but when mass is 0, classically there is this kind of symmetry, but it is also known that this symmetry is broken quantum theoretically. This is called anomaly, and but U1A is chiral symmetry, and but this is not completely broken when it is a charge. Yeah, thank you. Yeah. So we have a remnant of the chiral symmetry, and this is also known to be spontaneously broken.
The Gauss's law thing was like, that's how you, when you canonically quantize and how you restrict like gauge equivalent states, right?
Yeah.
The idea? Yeah.
Sorry, what was
The
it?
Gauss law on the previous
Yeah.
slide.
Yeah.
I don't know if people know what that means or whatever, but it's the idea of like, when you have like, if you canonically quantize and you have to take a slice through like gauge equivalent.
Yeah. Yeah. And but also if you know, if you run electromagnetism in school, university, so this is a Gauss law, and this means that the gradient of electric field is should be an electric charge. Electric charge density, and so this is a quantum. This equation is a quantum version of the Gauss law. Yeah, and originally, not all of the states can satisfy this one, and only there are only subset of states that can satisfy this one, and this is the physical state. Okay, and another symmetry is a bit advanced, and this is called the DQ1 form symmetry, and so what do you mean? What do I mean by one form symmetry? So typically, so for ordinary symmetry, we have a current and the current has only one index of space, and this is also in modern language. This is also called zero form symmetry. And recently there is a generalization of symmetry itself, and for that case, current can have another space index, and for this case, current is two form, and this is called one form symmetry. And so there is also further generalization of symmetry, but yeah. So anyway, there is a kind of symmetry. Yeah.
An anomaly here meaning like a symmetry in the continuum theory.
Yeah.
The classical theory that's not preserved quantum mechanically.
Yeah.
What anomaly?
Yeah. So anomaly means classically, we have this kind of equation, but if we consider quantum theory, then if we consider expectation value of this kind of operator, this is not zero. This sometimes happens in quantum field theory. Yeah.
That's just like a continuum back. We're not talking about the lattice at all, right? This is even just continuum space time, right?
Yeah. This typically appears in continuum space time. Yes. Yeah, and here I explain that so there is an anomaly, and then symmetry is broken, but sometimes it's not completely broken. Sometimes there is a discrete remnant. Yeah.
Spontaneously broken might also need a definition. I don't know. Oops.
Okay, spontaneous. Okay, so it's a very complicated. So spontaneous symmetry breaking means that it's not actually breaking, but it's breaking by ground state. So if we consider symmetry G, and then there is a operator which can generate symmetry transformation. Symmetry and the definition of symmetry. So quantum definition of symmetry is basically commutation with Hamiltonian. So this is the definition of symmetry. But sometimes if we consider ground state, and sometimes this operator sometimes ground state is non-trivially transformed under this transformation, and this is called the spontaneous symmetry break.
Like it's still a ground state, but a different one, right?
Yeah. That's good. Yeah, this for this case, typically we have a degeneracy of a ground state. And the number of degeneracy corresponds to a number of broken symmetry.
So some of the symmetries you explained, if we looked at the Hamiltonian that you wrote down before, we should just be able to see those. Like I think before you had now we have I mean, maybe I feel like the only working definition of a symmetry for some of the audience is this equation.
Right.
You know, something commutes with the Hamiltonian.
Right.
Yeah. I guess from the Lagrange perspective, like invariant under something.
Continuous thing, exactly. Yeah, you can rotate side bar as gone from the board.
And like zero form, or in this context, means like it's like
you have like Noether's theorem. You have Noether's theorem, Lagrangian, like whenever you've got a symmetry.
Yeah, but I think now maybe it's we need a definition of a symmetry now in the context of a Lagrangian.
Right.
I mean but maybe it's also too detailed. But just to appreciate the different kinds of symmetries. But I mean, I think that's very clear now. Like you can have like a Z1, Z2 plus Z2, Z3 Hamiltonian, right? Like it's the ground state, like the all zero, well, minus what I said, all zero, all one, all linear combinations, and then it breaks the symmetry.
Yeah. In this Lagrangian perspective, it's like an infinitesimal or Lie algebra action on the Lagrangian, right?
Yes.
Like, psi goes to e to the high theta psi, and it leaves L invariant. And then like just classical field theory language, you then get a conserved charge.
Yeah.
Like the J.
Yeah. Maybe but I guess somehow to see symmetries here, like for example, the fact that things are broken, like I have to look at the action, like the integral of this thing, right?
So then what you have to do is the quantum thing that Masumi's written on the board.
Right.
So then you have to do like a path integral with J mu inserted.
Yeah.
And then see if it's zero or not.
And then somehow, so I guess that means though, if I understand correctly, that just staring at L, it's not so clear.
The staring at L, you can tell the classical symmetry is completely
Right, but we want the quantum ones.
right.
But if I looked at H, I mean, I would only get the quantum ones, no? Except that maybe it's a Hamiltonian density, like it's in.
You still need to do some hard work.
So but okay.
Yeah.
Anyways, thanks.
Yeah. So in facilitator formalism, definition of quantum symmetry is a bit complicated. Yeah. So So we say, yeah, if this is non-zero, yeah, we say it's broken. But yeah, in general, it's hard to compute. Yeah. Okay. Okay. And here, so okay, this model has some accessible region by analytic computation, and so I'd like to explain what the accessible region. So, for example, if fermion is a very mass of fermion is very large, so basically we can ignore this term, and the theory becomes purely a gauge theory of gauge field, and it is known that this is Maxwell's theory, and it is known that Maxwell's theory is a free theory and exactly solvable. And there is also another technique called bosonization. This is particular in lower dimensional case, and so I don't explain a mechanism of this, but so it is known that the Schwinger model is dear to a scalar theory, scalar field theory with this Lagrangian. And here, meaning of parameter is different in the dual theory. First, G was a gauge coupling and strength of interaction, but this is mapped to mass of scalar field. But mass of fermion is mapped to strength of interaction. And when mass is zero, the scalar field becomes a free theory, and it's exactly solvable. And also, if mass is small, this can be approximated by perturbation theory. So this is an analytic situation. And also, if we consider Monte Carlo simulation, there is a side problem when theta is not small. So if we consider real-time case, Minkowski case, then so Boltzmann factor is exponential IS, so with highly oscillating integral. And if we consider Euclidean case, so we have a complex action. So when theta is not small, it's also oscillating. So conventional approach has a side problem. And so this is a summary of a map of accessibility and difficulty. So first, if theta is small, so we can use standard Monte Carlo approach. And when mass is very large, we can access by analytic computation. Also, when mass is small, we can use bosonization technique. But if theta is not small and mass is intermediate value, so we cannot access this region by analytic computation and conventional approach. So it's interesting to explore this region by quantum algorithm approach. Okay, so next let me put the theory of lattice. And there are various ways to put fermion on lattice. And here I use a formalism called stacked fermion. So originally fermion has two components, and in this formalism we put different components of fermion on different sides. And we also put the gauge field on link. So fermion is on side and gauge field is on link. And so this is a lattice version of the lattice version of the Schwinger model. So basically, compared to continuous field theory, differential operator is replaced by a difference operator. So this is a Lagrangian, and we have a commutation relation for gauge field and fermion. And this is a lattice version of Gauss law, and L corresponds to electric field. And so differential of electric field is replaced by difference of electric field. And we can eliminate the gauge degrees freedom corresponding to gauge field as follows. So if we take open boundary condition, meaning that lattice has a boundary, for that case, so we can solve the Gauss law in this way. So we can rewrite the electric field operator in terms of value of boundary and fermion operator. Also, we can take some gauge, and then Hamiltonian can be written in terms of purely fermion operators like this. Although it looks like complicated, but it contains only fermion operator. So this acts on finite dimensional elevator space. And so the first line is the same as the original Hamiltonian, and the second line was originally Hamiltonian for gauge field. But because of solving Gauss law, so we have a kind of non-local interaction between fermions. And next, I'd like to map this to a spin system. But before that, in our simulation, we'd like to measure compute the potential between heavy probe charge particle. And so here this slide is explained how to insert the probe charges. Although this may be too technical. So idea is that so in the community of large scale CD, so when we want to compute the potential between probe charge, so we typically consider this kind of a non-local operator. But here A is a gauge field, and the field strength F is a derivative of a gauge field, and then if we use a Stokes theorem, we can rewrite this operator like this. And but this one is the same as theta term, where theta depends on space. So, and here, so I include this operator as a part of the action and then switch to Hamiltonian formats. This corresponds to taking the parameter theta to be a kind of step function. Then we compute the ground state energy in this situation. Then we can compute the potential between the heavy charged particle.
Is the idea that if you know the potential, then you learn something about what phase the gauge theory is in? Like,
yes. I will explain this point later. Yeah. Okay. And next, I map the lattice system to a spin system. So problem is to rewrite this fermion operator in terms of spin operator such that we satisfy this commutation relation. And there are also multiple solutions of this problem. And most traditional one is called Jordan-Wiener transformation. So this is the X. This can, so solution is here. And we can check that if we substitute this operator to the commutation relation, so this operator satisfies. And then, if we insert this operator here, then there is a huge cancellation of spin operator. Then we get this Hamiltonian. So this looks complicated, but this is purely spin system. And so as a spin system, this is like XY model with longitudinal magnetic field with space-dependent magnetic field, plus some weird non-local interaction. So this is anyway, this looks complicated, but this is spin system, and so we can directly apply a quantum algorithm used for spin system. So this is a qubit description of the Schwinger model. So next, I'd like to explain algorithm path. So do you have a question for how to put the Schwinger model on qubit quantum computer? Okay. So next, let me explain an algorithm to prepare ground state. I think I don't need to explain. So I just here I'd like to explain what is the atmosphere of using quantum computer thing. And this is IBM screenshot of IBM quantum. And there are various ways to prepare ground state.
Actually, can I ask a question? So
Yes.
you very nicely explained. So now we just have a many-qubit Hamiltonian.
Yes.
What are the kind of physics questions now that you're interested in? You know, like what kind of observables would you like to compute? Or I mean, you can prepare the state, right? But then you also want to interrogate the state.
Yeah.
What is like interesting questions from a physics point of view?
Yes. Okay. I explained later. So one is to compute potential between heavy probe charged particle and so I explained that depending on parameters, behavior of potential has a qualitative difference. Yeah. Okay. I will explain. Yeah. And also, the field theory problem to consider some expectation value of operators under ground state is a very fundamental problem. Yeah. Okay. And so here I use algorithm called the adiabatic state preparation. And so here I start with some initial Hamiltonian, which is exactly solvable, and also for the background state is known and unique. And the second, I consider time-dependent Hamiltonian, which is initial Hamiltonian at the initial time and target Hamiltonian at the final time. And but we assume that if the capital T is very large, then the change becomes very slow. Then we use the adiabatic theorem, and which claims that if time-dependent Hamiltonian has a unique ground state with finite energy gap. Energy gap means a difference between fast excited energy and ground state energy. Then it is known that the ground state of a target Hamiltonian is obtained by this time evolution of the vacuum there of the initial state. And but practically we have to approximate this one. So first we have to take finite t, and also we have to discretize the integral. So we decompose it to a bunch of small time translation, and so this is technique. This may be too technical, but concretely, yeah, I chose the Hamiltonian like this. So we start with exactly solvable case, which is a massive fermion limit, and then we gradually turn on other parameters, and then when small t is capital T, so this becomes the original parameters, and the time evolution beta is approximated by circular decomposition. So next I will show what physics we found. So first one is a K1 case without the probe charge.
Sorry, did you explain like in your case what simple Hamiltonian do you use, and like
okay.
Expect that the gap is
yeah. The simple Hamiltonian is like this. So basically second term, so Hamiltonian without second term. Yeah. For that case, we have only Z operator, and it's exactly so. Yeah.
Did this have an interpretation in your phase diagram?
Well,
or is it like a different?
Yeah, it's quite defined because so this plays a role of lattice spacing. Yeah. So
they're not topping.
So it's kind of infinite lattice spacing limit. So it's not quite physical.
Do you like expect that as you increase W to the target value, the gap remains like that the path is a gap path? Or
Yes, yeah, it depends on parameter and
like how slowly you have to change it basically? Like is there like a physical intuition why it's not arbitrarily slow?
okay. So although intermediate regime is not trivial, but there is an expectation of phase diagram in this theory in continuum limit. So latest parameter is a theory like this, theory in terms of mass and theta. And the expected TG phase diagram is as follows. So this is theta compiled, and so at some point, people expect that there is a gapless or CFT point here, and also for some there is some line explaining some line describing the parity spontaneous broken phase of parity symmetry. And the generic expectation is that if the target Hamiltonian is in this regime, so we cannot use the algorithm basically, since even final state is not uniquely gapped. Yeah, but in this regime, yeah. So at least for final state, this should be uniquely gapped, and so we expect we can use it. Yeah.
And sort of on this whole path from W0 to W equals your favorite W.
Yeah.
W is like the adiabatic parameter in a sense, right?
Yeah.
So if there you expect that there's a uniform gap.
Yeah.
Does it scale with capital N with the discretization in the end? I mean, so
Okay. Good. For this regime, so the capital T does not scale as N. Yeah. But we found that okay. So in principle, this point can be also explored by adiabatic state preparation. But for this point, we have to scale T as a N. So generic expectation is that gap is like 1 over N, and then I think T scale should be scaled like N squared. So it's not very bad, but for this point, it's almost hopeless because the gap is like exponential minus N, and then T should be like exponential N. So for this case, I think we don't have speed up because of by quantum algorithm, but the gapless point could be can still have a speed up. Yeah. But in this talk, I will try to avoid this region. Yes. Thanks. Yeah. Thanks. And so I'll show numerical result. So one is one interesting observable is called chiral condensate, and this is the expectation value of psi bar psi, and after Jordan-Millikan transformation, this can be written in terms of Z, and this can be also written as a combination of a probability having each basis inside the ground state.
This is also the current for the chiral symmetry.
This is not the invariant of the chiral symmetry. So usually this is measured to explore spontaneous breaking of chiral symmetry. Yeah. So if chiral symmetry is not broken, and then this is zero. This should be zero. Yeah. there is a something in chat. Okay.
So naively, if I think about how I would measure this, well, I would prepare the state and then I would measure all the qubits individually and compute this alternating sum. I mean, like,
But
is there a sign problem?
okay, so for this case, this does not have a sign problem because ground state is almost like 0, 0, 1, 0, 1, 0.
It's oscillating anyway, so it's actually a
Yeah. So in other words, without minus sign has problem. But this okay. Okay. So I skipped some parts. So if we consider just the local expectation value of a local operator, we don't have this kind of stuff. So yeah. Instead of local operator, I consider the space averaged integral, and this and this should be the same if we have a translation symmetry. So if we want to compute local operator, just a local operator, so we don't have this problem anyway. Yeah. So it's just the bucket. It's just expectation value of Zn with that sum. Okay. So to describe continuum theory, we have to take infinite volume limit and also taking this spacing to be very small. And so before getting this result, so I made some kind of fitting to get the limit. But here I skip the details of the continuum limit, and this is the result for chiral condensate for massless case, and horizontal axis is edge coupling, and red line is the exact analytical result. So we see that there is an agreement within errors. And this is for massive fermion case. And now horizontal axis is mass. And there are two plots for both for theta equals 0 and theta equals 3 pi over 5. And straight lines are result of analytic computation by mass perturbation theory. So we see that when mass is small, there is agreement with perturbation analytical result, but when mass is not small, so there is a deviation. And for blue case, theta equals 0, and this can be accessed by a typical Monte Carlo simulation. But when theta equals 3 pi over 5, so Monte Carlo simulation is not practically available. So this is a kind of prediction of our simulation.
So the dots are, just to make sure I understand again, those are the
Numerical result.
Is numerical results.
Yes.
And the blue dash process.
Blue is for result for theta equals 0.
The other state up 3 pi over 5.
Yeah.
And then the red dots were tensor network.
There is a tensor network DMRG computation by this paper. Yeah. For theta equals 0 case. Yeah.
Can one, is there a challenge to doing the tensor network calculation for non-zero theta?
Yes. I have also done in last year. Yeah. I will briefly show the result later. Yeah. If we use the DMRG, so we can also use tensor. We can also exploit theta, non-zero theta regime. Yeah.
So I actually went with add something at both. Thanks for it.
Thanks. Okay, so next I'd like to consider non-zero higher Q case. in the presence of probes. Should I wait
Maybe
for
this.
Michael?
Yeah, let me go to it.
Yeah, Jonas is the only one online now, right?
I'm still around.
So, okay, yeah.
There's actually more people.
Oh, okay, okay. Maybe we should carry on then. I don't know. What do you think?
Oh, I mean, it's okay. Please just continue as you are. I'll.
Michael's only down for 1 minute.
Is that what he said?
I think so.
Quick pause.
I can get you more coffee if you want.
No.
And so the blue line in the previous slide was
yeah.
that was mass perturbation theory with Coleman's bosonization.
Yes.
That conformal perturbation theory, like it's conformal where masses. Is it just
No, it's not conformal. So
yeah, it's just free field theory.
yeah, it's free massive theory.
Okay.
Yeah, so it's different from sitting model.
The green dash line, that was what was the green dash one again?
This is also result of mass perturbation theory, but with non-zero theta.
Okay.
Yeah.
Right.
Yeah.
I see.
So the green dashed line is sort of a lower bound on what you would expect. And
I think not necessarily even a bound, right? It's only good.
Yeah, it's just approximation. Yeah.
Like the left of the diagram, the mass is small.
Okay, so let me explain this with probe charge. So first, let me mention there is an interesting problem called often called screening versus confinement problem. So let us consider potential between two heavy charged particles in the theory, and the charge of the probe is QP. And if we consider classical electromagnetism argument, the potential is simply like this. So this is nothing but the Coulomb law in 1+1 dimension, and it's proportional to distance. And so this also coincides with confinement behavior, in the sense that charge cannot escape to infinity. But it is known that this result is too naive, since Schwinger model has a dynamical fermion. So
QED in one dimension behaves like QCD, like it confines even.
yeah, in a sense it's similar. Yeah. So the confinement in 1+1 dimension is not so. It's quite ubiquitous, yeah, and also not non-trivial usually. And so there are some expectations from previous analysis using bosonization technique. So first, if fermion is massless, so it is known that potential behaves like this. So it's completely different from classical result. So it's exponentially decaying to constant. So this is called screening behavior. And the massive case is richer, and for long distance and small mass case, it is known that the potential behaves like this. So apparently, this looks like proportional to distance, but it's not always true. First, when probe charge is integer times charge of dynamical electron, so the slope becomes 0, and so this is again regarded as screening behavior. And when QP is not Q times the integer, so slope is basically non-zero, but sign is also not definite. So depending on parameters, sometimes this can be negative. So this sounds quite exotic behavior.
From the spin chain point of view, QP is just a parameter in the Hamiltonian, right?
Yes.
Yeah.
Okay. And And this picture is used for press release of my paper. So as changing parameters, sometimes opposite charge can feel repulsion. So the clever cat is surprised about. So let's explore this aspect by quantum simulation. But there are some frequently asked questions on this behavior. So first, I think you feel it's very weird because field theoretical thinking. So having a repulsion between opposite charge means that if we have a creation of a dynamical creation of electron and have a repulsive force, then so the opposite charge goes away to infinity. And if this can be repeated infinitely, so it seems that having infinitely many particles favor the configuration. So this sounds the theory itself is unstable. But this is not the case for the Schwinger model because this formula is saying that this kind of behavior appears when QP probe charge is not Q times integer, and when probe charge is Q times integer, there is always screening behavior. So this kind of thing does not occur. And another question is more complicated. So potential can be measured in the presence of probe. And then basically potential is a difference between energy with probe charge and energy without probe charge. And without probe charge looks ground state, but having a negative tension means the case with probe charge has a less energy. So it sounds strange. And there is a complicated explanation by the one-form symmetry, and basically answer is that if we are careful about one-form symmetry, Hilbert space is decomposed to some kind of superselection sector, and inside probe and outside probe the both are minimum energy state in a different superselection sector. So it is not right. Okay, so let's go to numerical result. So this is a case when parameter region when we expect the screening behavior, and this is a plot of potential both for massless case and massive case, and the symbols are numerical result for different volume, and the lines are dashed line is a result for large volume case, analytical result for large volume case, and the other lines are mass partition result for finite volume case. And we basically have an agreement, and also the behavior of potential is quite different from linear behavior. So it's not like confinement. So this is consistent with expected screening behavior. And also, this is a case when we expect confinement behavior. And red case is a massless case, and so we expect screening behavior. And for blue case, we expect confinement behavior. So this is basically linear behavior, and this is also consistent with expected confinement behavior. And finally, I'd like to show the slope of potential can be changed as changing parameters for some parameters. So if we change theta, when theta is small, slope of potential is positive, but sometimes zero and sometimes negative. So sign of tension could change as changing theta parameter. And this is a plot for energy density when we have a negative tension behavior. And the shaded region is inside between probe charges. And we are changing distance between probe charges. And this is the energy density as a function of position. So we see that indeed energy density inside is smaller than the outside. So we indeed have this kind of behavior. Okay, so let me summarize. So quantum computation is suitable for operator formalism, which is free from sign problem. But we have to deal with huge vector space, and quantum computers in future may do this job. And we have considered the ground state of Schwinger model with topological term. And we got agreement with chiral condensate with exact result and mass part ratio theory. And we also explored the squaring versus confinement problem and negative string tension behavior. And this is the outlook. And the problem in this talk involves only ground state. And this is the ground state in 1+1 dimensional theory. So for this kind of problem, it is known that the tensor network of DMRG approach is better than approach. So for this case, so we can take order 100 was 1,000 volume, 1,000 size. This is already published. And another interesting thing is although we consider the adiabatic seed preparation, but it is also interesting to implement other ways to prepare backend. And now we are doing a simulation finding energy spectrum including excited states, and it is also interesting to consider real time and finite temperature. And also, so with thumb and linear, so we'd like to study scattering for decay problem in fluid cell at some point. Also, I'd like to consider higher dimensional theory or bosonic theory, and I'd also like to include quantum error correction, mitigation thing, and at some point I'd like to find a nice problem which is not efficiently simulated both by Monte Carlo simulation and the tensor network approach, but I don't have a concrete idea yet. This is the final slide. So if we use the DMRG, so we can get much cleaner behaviors. And so I'm looking for a nice problem which where quantum approach has an advantage against the tensor network approach. So this is the end of my talk. Thank you very much.
Thanks so much.